So we're going to take a look at some more problems dealing with springs and energy. And so here we go. This one says, we're taking a look at a slightly different one, a bit of a different order here. So we are dealing with energy, but there are no springs in this one. This question says a 6.83 kilogram bowling ball moves at 2.58 meters per second. How fast must a 2.54 gram ping pong ball move so that the two balls have the same kinetic energy? Pardon me? So I've got a bowling ball, and it is moving through time and space. It has a mass of 6.83 kilograms, which I'd say is probably realistic for a bowling ball. That's going to be somewhere in the 15-pound range, which sounds pretty legitimate. We're talking about, well, a bowling ball. These are not exactly light. All right. It is moving with a worrying speed of 2.58 meters per second. Now that's not ultra fast. It's not a car or anything. That's probably about 7, maybe 8 miles per hour. Now that may not sound like much. That's faster than walking speed. Walking speed's about 3 miles per hour. In fact, that's probably running speed for most regular, well, comfortable people. So imagine that for just a moment. You have a bowling ball flying at you at a comfortable running speed. That's not the sort of thing I would prefer. In short, this actually has a decent amount of energy, the ability to make change. If that hits me in the face, it's probably going to break my nose. That's a noticeable change. All right, they say that there also exists a ping pong ball that has a mass of 2.45 grams. Now, the most common problem people run into on this is they just look at numbers and don't pay attention to units. I've told you many times in class, and I will repeat it, that numbers are borderline useless without units. If I walk into a store and you're operating that store, and you have something for sale for $2, and I think that I want it, I take it, grab it, and go over to the cash register, and I hand you a $5 bill for a $2 item, and you give me back 3 pennies, I'm not angry about the number. I'm angry about the units. In fact, most numbers are completely useless without units, and honestly, the units are much more important, most times, than the number is. Kilograms, we've got nearly 7 kilograms. That's a 15-pound bowling ball, which makes sense for a bowling ball. Ping pong ball, that is not kilograms. That would be a 5-pound ping pong ball. That wouldn't be a ping pong ball anymore. It'd be something else. Ping pong balls are usually very light. They're in grams. This is very lightweight, so you must pay attention to that. We want to find how fast the ping pong ball is going, such that they both have the same kinetic energy. So we want the kinetic energy of the bowling ball to be equal to the kinetic energy of the ping pong ball. That's what they're asking us to do. They want us to set it up where these two things are equal. Okay, well that means we're going to need 1/2 m of the bowling ball, v squared, equals 1/2 m of the ping pong ball, times its velocity, speed squared. So we can start filling some things in. Normally in class I point out that we want to put SI in, so we'll get SI out. So that's 6.83 kilograms times 2.54, I believe, meters per second squared. Was it 2.54? 2.58. I'm thinking of converting centimeters, apparently. 2.58 meters per second, quantity squared. Let's start by finding the kinetic energy of the bowling ball, and then we can start working with it. So I'm going to take this, and I'm going to find my kinetic energy. So I'm going to start off with 2.58. I'm going to square that, and I'm going to multiply it by 6.83, and I'm going to multiply that by 1/2. And I get the following: 22.73 joules. How do I know it's a joule? Well, meters per second squared is meters squared per second squared, times kilogram. We have a kilogram meters squared per second squared, which is joule. The other way that you can look at it is we put SI in, kilogram and meters per second, so we will get SI out. We're finding energy, which is measured in joules. Both of those are great ways to go about it, but you must remember that you only get SI out if you put SI in, which is going to be important for this next part, because we want 1/2 mass of the ping pong ball times its speed squared. We want these energies to be the same. So we have 1/2 not 2.45 grams. Grams is not the SI unit. So I'm going to convert that for you. It's 0.00, oops, nope, too many zeros. We have to divide by 1,000. There are 1,000 grams in 1 kilogram, so I'd move the decimal point over 3 spaces. 2.45, so that's 0.00245, if I'm not mistaken, kilograms, times VP squared. This is the most common problem people have. 2.45 divided by 1,000. Let me double check my numbers. Yep, looks good. All right, now I just need to solve for VP, so I'm going to take 22.7 divided by 0.00245 kilograms, and then divided by 1/2. That's a really big number. I get 18555.1. And I could go through, I could find my units here, but my units should be meters squared per second squared. Feel free to double check that. Which is good because it's equal to a speed squared, so that would be meters squared per second squared. I take the square root of everything, including the units, and we find that the speed should come up to 136.2 meters per second. Now that's incredibly fast. In fact, that's a really big number. That's actually going to be somewhere in the ballpark of, I don't know, almost 300 miles per hour, which may sound very strange at first, but I'm going to draw your attention back over to what we talked about before. First off, let's double check if I'm right. My solutions say that the answer is 136.2 meters per second, so that's looking good. Let's talk about why this is a big number. Energy describes the ability to make change in the universe. I told you, if we've got something barreling at me at running speed, and it's about 15 pounds, that would probably pretty easily break my nose. That is going to take a lot of energy to break my nose. If we've got a lightweight ping pong ball flying at my nose, well, if it's going a regular speed, it's just going to dink right off of me doing nothing. Remember, it's supposed to have the same energy, the same ability to make change. In other words, it's got to be moving fast enough that it will also break my nose, at which point you're going to have that ping pong ball moving incredibly fast. In this case, laughably fast. The ping pong ball is going to have a really hard time actually being put up to that speed. So it's an unrealistic number, but in that, we get an idea as to why it needs to be an unrealistic number, because it needs to have the same energy, the same ability to make change. In other words, the same ability to implode part of my face. And in order for something as light as a ping pong ball to do that, it's going to need to be moving incredibly fast.